Hello, welcome back to Algebra. In this lesson, the title of it is called Factoring the Sum of Cubes and Factoring the Difference of Cubes. So this will be the last section that we have on these kind of special cases of certain things to look for that allow us to factor certain special cases very quickly. In this case, it deals with when you have two terms that are cubed, means raised to the third power, and added together or subtracted. That's why we have the sum of cubes and the difference of cubes, because there's two different cases. So I split this one off into its own lesson because honestly you don't use these nearly as often in algebra. In the previous few lessons we've done difference of two squares, we've done perfect square trinomials. Those are used all of the time because a lot of times that has to do with quadratic equations, which is an entire branch of algebra that we use quite often and also in advanced math. Sum and difference of cubes, important, put it in your back pocket, but not something you're going to use as much. So pretty much what I'll do is just present what they are, and then we'll do a few problems to show you how you can use this to factor. All right, so what it's called is the sum and the difference of cubes. So what I'll do is I'll just write them both down, and what I'll do is I'll prove them to you. I'll show you what they actually equal down below and why they work, and then over here we'll work a few quick problems to show you how to use them. So basically what it boils down to is if you have some term, call it a, and you cube it, and you have that term added to some term, call it b, and that one's also cubed, this is called the sum of two cubes. Now a can be anything. It can be a variable cubed, or it can be some expression cubed, or whatever. B can also be anything. It can be a number, it could be an expression, it could be a variable cube. But any two times you have two guys like this added together that are cubed, it can always be written as follows. As a, whatever a is plus b, these bases here, multiplied by this polynomial, a squared minus ab plus b squared. Now I'm going to show you why this works in just a minute, but for now let me just get them on the board and then we can kind of like go off and talk about why they exactly work. But if you identify that something looks as if it fits into this form, or if you could rearrange things and force it to legally with the rules of algebra, write it in terms of this, then you can just write the answer straight away. This is the factored form. Similarly, if you have a cubed and you subtract off b cubed, so you have the difference of two cubes, then it looks like this. It's very similar, as you might guess, a minus b, and then over here it's a squared plus a times b plus b squared. So you can see the differences between the two here. When you have a plus sign between the two cubes, the first term here is plus, and then you have a minus sign in the trinomial. And then when this guy is minus here, then it causes a minus sign in the first binomial out here, but then this flips to a plus sign. So try to remember these, try to memorize them, but honestly, you don't use them that much, so it's kind of better. Honestly, I just think you just know that they exist. If you ever need to solve an equation or do something with the difference of cubes, you could probably just look it up. It's not something I have memorized from when I was in algebra a long time ago, but I do know that the sum and difference of cubes is something that is a nice form that can be factored in this way, so I know that it lives somewhere and I can look it up if I need to. But for now, we're just going to put these on the board, and I want to spend a minute showing you why they work. Let's just start with the tail end of here. We're saying that a cubed plus b cubed is equal to this. So what I want to do over here is I want to take and draw a little arrow here, and let's talk about the first one. What if we have a plus b multiplied by a squared minus ab plus b squared? And I wanted to ask you to multiply this out, right? How do you do it? You have a binomial times a trinomial. We've done this many times. You take the first term, a, distribute it into each of the terms. That'll give you 3 terms. Then you take the second term, b, and you also distribute it 3 times, which will give you 3 more terms. So you expect to see 6 terms, right? So let's go ahead and do that now. A times a cubed, or a squared, is going to give you a cubed, and then a times negative ab will be negative a squared b. You add those exponents on the a. A times b squared is ab squared. Okay, that's the first 3 terms. So we're done with this. We move to this one. B times a squared is a squared b. I can write it as ba squared, but I'm going to flip it around to a squared b so it'll match this one here. And then b times negative ab will be negative ab squared. And then b times b cubed is going to be, b squared will be b cubed. So 1, 2, 3, 4, 5, 6 terms. But notice what's going on. This term here exactly adds up with this one because this is a negative and this is a positive, so we actually get a 0 when we add those up. And then this term here exactly adds with this one, also giving you 0 as well. AB squared negative AB squared. So the only term that actually survives here is the very beginning term and the very end term, which, as you might expect, is exactly what we were trying to show. So here we know that A cubed plus B cubed. So what we proved is that if we take the right-hand side of this guy, multiply it all out, cancel it all out, what we get is this. So we've proved it by going backwards, but essentially you can think of it this way. Anytime you see something like this, you can automatically know that it's the sum of two cubes, or if you see two things that are cubed and added together, you know that you can write it in its factored form like this. Remember, the factored form is basically looking at an expression and trying to figure out what two things can be multiplied together to give you that. So if you ever see something like this in a problem, you can write its factored form because you know that it's always going to look like this. We've gone through and showed the cancellation. And just for kicks and to give us a little bit of practice with this, additional, let's take a look at the second one. And we're saying that this guy is going to multiply to give us this. So we have A minus B times A squared plus AB plus B squared. Now it's the same sort of thing. Let's multiply it out. What we have is A times A is A cubed again. A times AB is going to give us A squared B. A times B squared is going to be AB squared. Now this is a negative B here. When you multiply by the A squared, you get not a plus sign, you actually get a negative A squared B because you're multiplying a negative times a positive. Now this times this guy gives you also a negative, but it's AB squared. You add those exponents on the B's. And then this times this is also a negative. B times B squared gives you negative B cubed. So then we go and look at exactly the same thing. We say, well, we have this guy here, AB squared matches this term, but it's negative and positive, so they cancel. And then the AB squared goes over here and cancels with this one because it's a positive and a negative, so this gives you 0. So the only thing that's actually left in the entire thing is A cubed. Everything's gone, but I do have a minus sign, B cubed. All right, so we've shown that when we take the right-hand sides of these guys, we multiply them all out, and we can show ourselves that the left-hand side must equal the right-hand side. That's why I'm doing it. Most books will just write this down and say, just use it. But I don't want you to think that these things come from nowhere. Now you might say, well, how did they know that it was like this? How did they just make this up? Well, it didn't make it up. A lot of people who worked on math over the years, over the last few hundred years, have looked at special cases of equations and make it their life's work to figure out what they could set it equal to. How could they manipulate it and make it simpler or make it useful? And so someone a long time ago sat down and figured out that this was the correct form, and they probably did it by backwards multiplying and showing that you can get the left-hand side equal to the right-hand side. Now what we're going to do is use these to factor things. We know A cubed plus B cubed is equal to this factored form, so let's take a look at a practical problem and see how we would actually use it. Let's say I gave you a problem on a test that looked like this, t cubed minus 27, and I say factor this expression. The very first thing you're going to do is try to figure out what is common to both of these terms. What can I pull out? Well, I have a t cubed, I don't have any t's here. I just have the number invisible 1 here, and there's 27. I can't pull anything else there. So then you say, well, I'm done. I can't really factor anything out. But then the next thing you do is you start looking at special cases. You notice right away you have a cube, and this 27 should start ringing bells. Remember I told you when we did difference of two squares and the perfect square trinomials, I said certain numbers should kind of get your alarm bells ringing, your sense, your spider sense, if you want to call it that, right? You should start thinking about things. When you see numbers like 4, that's 2 squared. When you see numbers like 9, that's 3 squared. 16, 25, 36. You can keep going. Those are the perfect squares, right? So that you need to also start thinking about what cubes would be. And this is one of those things that comes with practice, right? So 27 actually is a special number because you can write that as what? As 3 cubed, right? And that's something that you may not realize until you do this stuff a lot, but why is that the case? Because 3 cubed is 3 times 3 times 3. The first two 3's multiply and give us 9, but 9 times 3 is 27. So 27 is called a perfect cube, just like Just like, 16 is a perfect square. 4 times 4 is 16. 27 is one of these perfect cubes. So you're going to run into some of these perfect numbers as you go on through math. And we'll do a few, in the next problem I'll show you another perfect cube, but probably one of the most important ones of the low numbers anyway is 27 being 3 cubed. So when you write it like this, it's obvious. It's the difference of 2 cubes, and we have a rule for that. Anytime you have something cubed minus something cubed, you can always write it like this. A in this case is just t, the first variable, and b in this case is going to be the number 3. So basically in this example here, a is going to be equal to t, and b is going to equal to 3. So we can write the answer straight away. It's going to be, well, I'll just write it down as is written over there. It's a minus b, and then it's a squared plus ab plus b squared. Right? But we now know that a is t and b is 3, so we just stick it in there. So what we have is t minus 3, and then we have t squared plus ab, which means t times 3. So let's write it as 3t plus b squared, the last one squared here. And in the last step, we'll just simplify a little bit. T minus 3 t squared plus 3t plus 9. Let me double check my math here. T minus 3, t squared plus 3t plus 9. That's the final answer. How did we know that was the final answer? It's because the problem was given to us as a special case, right? Up till now, we've only been factoring these binomials and things as special cases. Are they perfect squares, right? When you have the number 16, you know it's a perfect square. 4 times 4, it's a beautiful number. 25 is a perfect square. 5 times 5. 27 is a perfect cube. 3 times 3 times 3, meaning 3 cubed. And some of these binomials are just, they're the difference of 2 cubes, or the difference of cubes. And when we have a difference of cubes, we know that a very special factored form is always true. So we just figure out what the things are and we stick it in there. We don't have to do any more work. We could multiply all this out, and when we do, we would get this. I'll leave that to you. We kind of already did it on the other board, so I don't feel the need to do it again. But that's how you would use it in an actual problem. So let's take a look at another problem. Let's say you have 8 times p cubed plus 1. And I told you, I want you to factor this. The first thing you do is you say, well, what's common to both? You don't see anything because there are no p's here, no numbers that seem to can come out. But this p cubed should be a clue to you. You should at least start thinking about cubes. Right? But it doesn't look like it's anything special here because of number 1. But then you realize, wait a minute, number 1 can be written as 1 cubed, right? I mean, when you think about it, the number 1 cubed is just 1 times 1 times 1, which is just equal to 1. So this number 1 can be written as 1 cubed, right? So you might say, all right, it could be written as 8p cubed plus 1 cubed. And then you look at this and say, well, this is pretty close, but it's not quite the sum of 2 cubes. I mean, this is a cube, but what about this 8 up here? Well, just like I said with the 27, you need to have your little awareness go off. 27 is a perfect cube. 3 cubed, 3 times 3 times 3, that's 27. You're going to end up needing to know that. It turns out that the number 8 is one of those special numbers that you'll just learn over time. It's also a perfect cube. When you think about it, the number 8 can be written as 2 cubed. Why? Because that would be 2 times 2 times 2, and you all know 2 times 2 is 4. 4 times 2 is 8. So 8 is actually a perfect cube. So because it's a perfect cube, I can write it like this. Wrap it in parentheses, 2 times p quantity cubed plus 1 cubed. And now it's very clearly the sum of 2 cubes. The quantity a up here in our little rule is what's inside of here. 2p, that's what's being cubed. The quantity b in our little rule up here is just the number 1, that's being cubed. Why does this work? Because this exponent applies to the 2, making 8, and that applies to the p separately. You kind of distribute the exponent in, giving you 8p cubed. So you can go over here and remind yourself that when you have the sum of 2 cubes, it's just the sum of a plus b, and then a squared minus ab plus b squared. Right? So then you can apply that straight away. So what it's going to be is a cubed plus b cubed. This will help you memorize them a little bit over time as well. So let's just write it down. A plus b, and then a squared minus ab plus b squared, where a and b are given just like this. So then we will just substitute in what we know. A is this, so inside of here it'll be 2p plus b, but just number 1. And then over here we have a squared, so you got to be careful though, because when we say a squared, it's the quantity 2p, the whole entire thing is what's actually squared. Because the value of the quantity that's cubed here, the base, for lack of a better word, is 2p. That's what's being squared. So write it like this for now. And then minus a times b, 2p times 1, 2p times 1, that's a times b. And then plus b squared. B is 1, so I'm just going to write it as 1 squared. Now in the next step, we'll just simplify it a little bit further. 2p plus 1. What is 2p squared? The exponent is going to apply to the 2, giving 4, and then it'll also apply to the p, giving me 4p squared minus 2p times 1 is just 2p plus the number 1 here. Let me double check my answer. 2p plus 1, 4p squared minus 2p plus 1, that's the final answer. So it all becomes a game, basically, when you're trying to factor these things. First, trying to pull out what you think might be common, but in these cases, nothing is common. You can't pull anything out, so you look for special cases. You might not immediately see if it's the sum of 2 cubes or the difference of 2 cubes, but you can use the rules of algebra to write it as the sum of 2 cubes and the difference of 2 cubes. If this number in the problem, for instance, instead of 8, if it was 7, then I would never be able to do this problem, because it only works that I can write this thing as 2p cubed. But if this were 7, I would not be able to do that. I would not, because 7's not a perfect cube, right? Or if this number over here, instead of 8p cubed plus 1, what if it was 8p cubed plus 2? That wouldn't work. It wouldn't be the sum of 2 cubes, because I would not be able to write this as a cube at the last part of it here. So you see what I'm trying to drill in over and over again is that these are all very special cases. And the next few lessons we'll be factoring things that are not special cases. We'll take the training wheels off and let you go and do things that aren't just special cases. But for now, we're just doing things that are very specially constructed to be one of these special cases here. So what if we have x to the 6th power plus y to the 3rd power? And I say, hey, factor this. First thing you do is say, well, what's common to both? Well, here's a bunch of x's, here's a bunch of y's. I can't pull anything out. You do see a y cubed, and that makes you think maybe it is the sum of 2 cubes, but this is obviously not cubed. So you look at it and you say, well, it's not the sum of 2 cubes. I have no idea what to do. But then you need to start thinking. That cube here is probably not an accident. They're probably trying to get me to use the sum of 2 cubes. So I need to use the rules of algebra to write it in terms of the sum of 2 cubes. Is there any way that I can write this legally to make the first term a cube as well? And the answer is yes. Why? If I write it as x squared, but also raised to the 3rd power up here, and then write it like this, then it is the sum of 2 cubes. And why is this legal? Because when I have a power raised to a power, we've done this before, you just multiply the exponents. 3 times 2 is 6. So x to the 6th power is, or can be written as x squared to the 3rd power. So then I have a cube term added to a cube term. So then I can use what I've already used over there. But now I know that a in our little formula there is just x squared, and b is whatever is cubed over here, which is y. And if you remember, for the sum of 2 cubes, when it had x cubed plus y cubed, then what I had was, it was a plus b, and then it was a squared minus ab plus b squared. That's what happens when you have the sum of 2 cubes. So then you can just go and plug in straight away. We now know that a, whatever it is here, look here, I put x and y. I'm sorry about that. That's confusing. It's a cubed plus b cubed, and this is what it would be equal to here. So now we know a is x squared, so I'm just going to stick it in here and say, well, it's going to be x squared plus whatever b is. And then over here, it'll be careful, a is x squared, but that's also squared. So the best way to write it is x squared squared. Whatever the a is, which happens to be x squared, is what is raised again to the 2nd power. Minus a times b, which is x squared times y, plus, again, b squared, but b is y, so we'll make it y squared. Now in the final step, we'll just do a little simplification, x squared plus y. Here, x squared squared, you multiply the exponents, giving x to the 4th power, minus x squared times y plus y squared. And this should be the final answer. Let me double check. X squared plus y, x to the 4th minus x squared y plus y squared. So that is a good introduction to the sum of cubes and the difference of cubes. Again, they're special cases. What you should do is try to see if you can identify cases when you can write an expression as the sum of 2 cubes or the difference of 2 cubes. And if you can, then we have some handy some handy relations that have already been worked out that we've shown are true, that if I can write them like this, then the factored form will be this, and so on. Now what we'll do in the next lesson is we'll just work a few more problems, slightly higher complexity, but the same idea will hold. We're going to try to manipulate expressions into sum or difference of cubes and then write their factored form. And then after that, we'll take the training wheels off and teach you how to factor expressions that do not fall into one of these special cases that we've discussed so far.